I'm going to do something a little bit different today, and that we're going to do like a little historical development. Usually in physics class, we just tell you what the final word is on it, how the science works in our kind of modern way of understanding it. But what I want to do today is introduce to you quantum mechanics from a historical perspective. And the reason for that is because quantum mechanics is really unintuitive, right? And it's hard to just approach it kind of as an abstract theory. So I think it's really kind of important to understand the foundational elements of it that all happened the very early days of the 20th century, and of course grew to define the entire, digital revolution is only possible because of our understanding of quantum mechanics. So it starts with kind of a story that's happened several times in physics, in that we reach a point as a society, as a scientific body, where we think we pretty much know everything. And invariably, when that happens, some little nooks and crannies of some weaknesses in theories or some unexplained phenomena eventually grow to sort of overwhelm the entire body of knowledge, and you have this big revolution, right? So in the late 1900s, we were in that situation where people had just figured out how electricity and magnetism works, and everyone was feeling pretty confident that the body of knowledge of physics was complete. But then they started seeing a lot of experimental results, some of which are listed here, and I'll talk about in more detail, that couldn't be explained with what we now call classical physics, right? So classical physics would be pre-20th century physics. That is physics before Einstein introduced this to relativity and before quantum mechanics came to take the center of the stage. So one of the first problems that, at first didn't look like a big deal was about the spectrum emitted by a hot object, right? So, a cooler flame will glow red, and a hotter flame will glow blue, and things like that. And the sun is white, and so people were trying to model, as a function of temperature, exactly what the colors emitted should be, right? So, they wanted to have a chart like this: intensity of the release of light versus the various wavelengths, right? And kind of an embarrassing thing happened is, if you apply classical physics and what you know about waves and wavelengths and stuff like that, you get something that became known as the ultraviolet catastrophe. Because what you would say is, if you have a temperature comes from molecules and atoms vibrating. There's a whole spectrum and a host of vibrations that are possible, from very short ones to very long ones. And so the really short ones would release very small wavelengths, and since you could go all the way down to zero, the wavelengths would actually be getting smaller and smaller, which takes you out of course, the blue and into the ultraviolet, which is why it's called the ultraviolet catastrophe. And it theoretically would blow up and go to infinity, right? Which makes no sense. A finite temperature object should not be emitting an infinite amount of UV radiation, right? So this is called the ultraviolet catastrophe, right? People were pretty desperate in the late 1890s to try to fix this. And one of the preeminent mathematical physicists of the day, Max Planck, took a stab at it. And he solved it, okay? Now, what he did, he considered to be kind of a mathematical trick. Blackbody radiation is the kind of physicist code for the light that is coming from an object uniquely because of its temperature. In other words, it would look black to you if it didn't have a temperature, right? Because most of the time when you're looking at something, you're looking at reflected light. So forget about the reflected light and just think about, because it's glowing or whatever, because of its temperature, how much radiation is coming out of it. That's what we mean by blackbody radiation. So the trick that Planck came up with is he had this idea, which was really kind of just a mathematical trick, is that he said, I'm not going to let the energy be continuous anymore. He introduced this n here, which is an integer, right? So it could be 0, 1, 2, 3, right? And he allowed the energy to come in multiples, integer multiples of the frequency. And he had to put a scaling factor in here. I don't know if he used h, but anyway, traditionally it's h, and that would scale the frequency to energy, right? So it'll give you joules per hertz or something like that. And once he did this to the energy, it turned out all the math equations went from being continuous functions to discrete functions, and it actually fixed the problem. And you would get these nice curves that peak and then fall back to zero in the UV, and it corresponded to experimental results and everything. And by looking at some experimental data, you could fit the value for h, and what he thought as a one-off experiment is now known as, of course, one of the three most important fundamental constants of the universe. It's named after him, Planck's constant, right? The other two are the speed of light, c, and universal gravity, capital G. So he published this. He wasn't, he solved the problem by using a math trick, so he didn't really feel that he had advanced the body of understanding, scientifically speaking, but it was an important paper, right? But people kind of puzzled over why this would work. People didn't think about it physically, in other words. Now, around the same time, there was another issue called the photoelectric effect, which is an experimental result, which people had seen in the lab and they could not explain. So let me unpack that. The so-called photoelectric effect is that there are certain metals or other materials that hold on to their electrons very loosely, right? So metals, we know, have the valence electrons they're good conductors. That means each individual atom is not holding onto those electrons very well. And so it doesn't take a lot of energy to free those electrons, right? That's what that means. And if you shine light on there, right, some of the light could be absorbed by an individual electron, give it energy, and the electron might pop off, which could now that we understand electric fields and all that kind of stuff, could be easily detected, right? So people were trying to investigate systematically the relationship between light shining down on a metal, these photosensitive materials they're called, and the electrons popping off of there. The results really didn't make sense, okay? So what are some of the things that didn't make sense? Well, first of all, there was a cutoff frequency. And what I mean by that is the frequency of the light was critical. If the frequency was too low, then no matter what you did with the light, you could never get an electron off, right? So in other words, like let's say this particular metal needs orange light, right? And if it's red light, it doesn't free an electron. Well, the physicists of the day would be like, well, let me just get a stronger red light. Let me make it a really bright red light with high amplitude waves. And that's a lot of energy, but that still would not free any of the electrons, right? And as soon as you cross that threshold frequency, you would always release electrons. But the energy, they would capture these electrons and measure their energy as they flew off the metal. The energy of each individual electron didn't change if you made this light brighter or dimmer. In other words, once you pass the threshold frequency, the electrons always popped off with the same amount of energy. Now, you could give these electrons more energy by increasing the frequency of the light, right? So this whole idea of the frequency dependence and having a hard cutoff like that and the frequency related to the energy, it really did not make sense to people. And the fact that if they did raise the amplitude, like make the light brighter, it wouldn't affect the energy of individual electrons, but it would pop more electrons off per second, so the energy would get distributed. Now, this idea of relating the frequency of light to the energy of the electrons, if you're a really smart guy named Albert Einstein and you've read this paper by Max Planck, you're thinking, here's something to it, right? So what Einstein does in 1905 is he publishes a paper, and this is actually the paper that made him famous within the physics community. He did this in 1905. That's his so-called miracle year. He published 3 or 4, depending on how you want to count them, papers, any one of which would have been worth a Nobel Prize. But this is the one because it had hard data and it was a world-class explanation that put a lot of things together. This is the one that was a real big breakthrough for him. What he did is he went back on the idea that that light is a wave. He said, well, we have a real successful model of light as a wave, right? We can see interference patterns, we can measure the amplitude, we can talk about its frequency. But Isaac Newton, back in the day, he thought of light as being made out of small particles. He called them corpuscles or something like that. And so Einstein said, well, what if there is something to that model? Let's go back to that model, which nobody else in the early 1900s would dare to do because the fact that light was a wave was well established by Maxwell's equations and all that kind of stuff. And he said, well, let's do this. Let's say that the energy of a single photon is exactly what Planck was talking about over here, right? In other words, this n, it's not just some arbitrary integer. You're counting photons, and each photon is the term for the particle of light, has the energy of h times f, right? So what the frequency is telling you is actually the energy per photon that comes in. So when you shine red light on there, instead of thinking about it as a wave, think about it as a lump sum of energy equal to h times the frequency of the light, right? And as you raise the frequency, you are raising the energy per photon, right? Think about light as a stream of bullets. And now all of a sudden things start making a little bit more sense, right? If the red light, if each bullet does not have enough energy to free the electron, right? It's less than the ionization energy of the electron, then it doesn't matter how many you shoot down. Each red bullet doesn't have enough. And then, so it gets absorbed in some other way, like thermal energy, or, goes into the material. But once you cross the critical threshold, that is, you have an energy per photon that's greater than the ionization of the electron, then you'll be popping the electrons off, right? And they would all come off with the same energy as long as the color of the light is the same, right? Same frequency light, same energy per bullet, same amount of energy to give to each electron. And so here's what that means mathematically, right? This is just conservation of energy, right? The HF, that's the energy that you have in the light, in each particle of light, each photon. And then it gets absorbed by the material. That requires a little bit of work. So physicists would put work here. A chemist would say the ionization energy, right? That gets used up to free the electron, right? That's a type of potential energy, right? Electrical potential energy. And then the leftover joules is what can give the electron kinetic energy, right? So if you want to find out what the actual work function or ionization energy is, you just set HF equal to the W, right? So the work function is a property of the metal, right? It has to do with the atomic structure and the atomic conduction layer bands and all that kind of stuff. It's chemistry, basically. HF is the energy per photon, and the kinetic energy is what's left over. So if HF is smaller than the work function, then you can't get any kinetic. Kinetic energy can't be negative, and so you just don't have any electrons freed. And so this equation actually gives you a cutoff frequency and gives you a linear proportion between frequency and the energy of the electrons, and that's exactly what we saw experimentally. So what Einstein did is he took Planck's idea, and said, no, this isn't a mathematical trick. This is telling you something physical about the way the universe works, right? That things are quantized. Light is quantized into chunks, just like charge, right? Same thing happened to charge, if you recall. People used to think that charge was a continuous function, right? That's the way Ben Franklin, those guys thought of it, some kind of fluid. People used to think matter was continuous. This is just one more chapter in that story of human beings think everything is continuous, but actually it's made out of small discrete packets, right? So this is the image that I like. When you hear the word quantize, you think you can have a continuous ramp where you can put the box anywhere you want, but in a quantized world, you think about it as a stairwell, and the box can only go on one of these steps. There is no in-between spot, right? So in this world, we would say each step is HF, right? Or if you're thinking about charge, you'd say each step is the charge on a single electron or a single proton, which is the same amount. So this is considered the beginning of the quantum revolution, right? Quantizing things that you thought were continuous. Another thing that happened in the early 1900s is that Compton was a famous experimentalist, and he was doing a lot of experiments with X-rays. And one of the experiments he did is he would shoot an X-ray in, which, if you're thinking about it as a wave, you would say, once again, you're going to think about how an electron would absorb a wave very differently than if you think about it the Einstein way as a particle. And the experiment that Compton did cannot be explained unless you think about the photon as a particle. And that is, the incoming X-ray comes in, hits an outer shell electron, knocks the electron free from the atom. Compton would measure the momentum of that, the speed and direction of the outgoing electron, and he would then also detect the X-ray that emerged after the collision. Now, according to classical physics, right, a wave is a wave is a wave. A wave comes in and reflects off of something, it comes out at the same frequency. And what Compton discovered is that the frequency was lower. And not only was it lower, but it changed as a function of angle, right? As the electron would scatter one way, the scattered photon would go a different way. And then he had this brilliant idea of saying, well, why don't I apply conservation of momentum and treat this like a collision between two cars? You have an incoming photon, which is car A, hits car B, which is the stationary electron, and then afterwards they're both going, and the X components and the Y components have to match up. And he did, and he modeled that as the momentum is equal to Planck's constant divided by the wavelength. And so that is very similar, and he, of course, was inspired by Planck saying the energy is proportional to the frequency, right? So he used that equation and used the wave equation, frequency is equal to velocity divided by wavelength, and came up with his quantization of photons to explain the scattering effect, the so-called Compton scattering afterwards. Now, the same year, right, so it's all the rage here to be quantizing things that you think are continuous, right, to think about light as made out of particles. De Broglie, who was a PhD student in France, had this genius idea. This was actually his PhD thesis in 1923, where he said, well, why don't I take Compton's idea and run it backwards, right? Nature is very symmetric. If things that we think of traditionally as waves can act like particles, then what happens if I take Compton's relationship between momentum, right? This equation, the P down here is for momentum, lambda for wavelength, and there's Planck's constant coming up. Planck's constant is in every quantum equation. Why don't I just run that backwards and take a classical object that has momentum, has a mass and velocity, like a single electron, and assign it a wavelength? Can I find some features of an electron that would demonstrate wave-like properties? And it works, right? This is kind of amazing. We didn't do Young's two-slit experiment this year, but this is considered one of the definitive proofs that light is a wave. If you shine light through two holes like this, you will actually get an interference pattern where you get, constructive, destructive, constructive, and destructive interference. So this is a well-known phenomenon to demonstrate that light is made out of waves. And so after people read de Broglie, or maybe de Broglie had suggested people could do this experiment, he was not experimentalist, so he didn't do it himself. In fact, the experiment, I think, wasn't done until years later. It's very hard to do. But eventually they could make slits small enough and have electron sources precise enough that they could actually do this experiment. And it turns out if you throw a whole bunch of electrons at two slits, instead of getting what you'd expect from particle theory, that is, a big lump of electrons that came through the bottom window, piling up here, and a different lump through the top one over here, you actually get an interference pattern, right? I mean, just stop and think about that for a second, right? You're throwing particles of matter, or at least what we traditionally thought of as particles of matter, and you're measuring constructive and destructive interference in places that wouldn't make sense if you actually model this as mass and velocity. However, works perfectly well if you say, oh, that electron is a wave with this kind of wavelength. Something even cooler that de Broglie did is that once he realized what these wavelengths were, he actually had a contribution to orbital theory. He's like, why are there only certain stable orbits, right? Which I'll talk about in a second. And he said, oh, those actually correspond to integer multiples of the wavelengths of those electrons, right? So like the n equals 1 is one wavelength, and n equals 2, right? I'm talking about the rows on the periodic table here. And this, matches pretty well for hydrogen. So this whole idea, that's another quantization thing that you know about from chemistry class, right? When they did spectroscopy, the surprising result is that these atoms don't just emit any energy, they have discrete energies that are given off, right? So that indicates something quantized about the structure of the atom itself. And of course, now we know that the way we think about this is that there are certain allowed orbits, right? It's not like planets around the sun that you can orbit, or satellites around the Earth that you can shoot up to any height and give it the right velocity and you'll get a stable orbit. Electrons around the nucleus and the atom cannot occupy any place they want, and there are only certain stable orbits. And so de Broglie's explanation for that would be these standing waves. However, the one that really took off was Bohr. Bohr actually solved this problem by quantizing yet another quantity. He said, hey, if energy is quantized, if Compton can quantize, photons to have discrete momentum and all that kind of other stuff, he thought, well, another conserved quantity is angular momentum, right? And these electrons are going round and round, so maybe I should quantize the angular momentum. And by quantizing the angular momentum, he actually matched the orbits to the experimental data really well also. And then another kind of crazy thing that was observed to happen in the early 20th century that is pointing to this idea that it's naive of us to think of things as either waves or particles, but actually it's kind of some kind of blurring of the two, is physicists started observing something called pair production, right? So what does this mean is if you think about a photon as having a certain amount of energy, right? So equal to h times the f times the frequency. and you think about that as a particle, and you also think about electrons are kind of like wave-like and kind of particle-like also, as long as you obey the conservation laws, that is, you observe the conservation charge, right? So a photon has no charge. So if you're going to make something with charge, you have to make something with the opposite charge. So the total charge is still zero. Um, then there is no actual rule in physics that prevents a wave turning into particles or particles turning into waves, right? As long as the energy is the same before and after, the charge is the same before and after, and the momentum is the same before and after, it can happen, and it does happen, right? So not only can we model electrons as waves or particles, or light as waves or particles, but we can turn light into particles and particles into light. It's really kind of amazing. And so this was the state of affairs in the early 1900s, and Bohr led the group of physicists working on this problem. He's considered like the grandfather of quantum mechanics. And in the 30s, they had a series of meetings where they tried to puzzle out, like, what are the new rules of the game, right? And Bohr, to a certain extent, put in the final word. I haven't really heard anybody come up with anything better about how to rectify the idea in your head that things are not just waves or particles, but the ultimate reality of nature is that things are both particles and waves. And what Bohr came up with was this idea of complementarity, and that is that a particle is both a part. Everything is both particle and waves at the quantum level, right? If you go small enough, and which attribute you see will depend on what experiment you run. If you run an experiment looking for wave-like properties, then that's what you see. And if you run an experiment looking for particle-like properties, then that is what you will see. And this is one of my most, this is probably my favorite quote of all time for not just physics, but everything, is that the opposite of a correct statement is a false statement, right? But the opposite of a profound truth, right? We're not talking about something correct, but something that is deeply rooted in how the universe works. The opposite of a profound truth may well be another profound truth. Just think about that one for a while. Now, this was not the end of the story. You couldn't just say waves are particles and particles are waves. You need to have a mathematical theory, and that would come in these years and in the following years with Schrodinger and Heisenberg, and Feynman would come up with three alternative explanations for quantum theory. And, even then they knew they needed more because they couldn't actually do the spectrum of complicated atoms. They hadn't figured out, the electron spin, which you learned about in chemistry class. You could see that in spectroscopy sometimes, and they couldn't understand it. There was no mathematical formalism, right? Some spectral lines are sharp, some are the diffuse, right? That's where the S, the P, and the D come from, is describing these spectral lines. They couldn't predict that with wave-particle duality, all kinds of stuff, right? However, nowadays, this is math that's sort of beyond what we do in high school, but with the Schrodinger's equation and Heisenberg's matrix formulations and Feynman's path integrals, we do have a complete theory for quantum mechanics. It doesn't mean that we understand that we have a way of visualizing all this stuff, right? But we do have math that will give us the correct predictions for experiments that we run, and that's how the entire digital revolution goes forward, and we keep making smaller and smaller semiconductors and all these other kind of things. It all started way back at the turn of the century, I should say the turn of the previous century, with some very small little problems that turned out to have huge consequences. Okay, thanks for listening.